Now we'll move on to the quotient rule. The quotient rule gets its basis from the product rule. We're going to consider the following case. Consider cap f of x to be little f of x over little g of x. Now in a little while, we'll come back and call this a high and a low. You'll see why in a little while. But let's just look at cap f of x equals little f x over little g of x, and we're going to find f prime in terms of little f and little g. Now, the thing is, all we know from the previous part of the lesson was product rule, and we do not have a product. So since we only know product rule, let us change this equation to one where we have a product. So big F of x times g of x equals little f of x. Now we're ready to use our product rule. F times g prime plus g times f prime of x equals little f prime of x. I took the derivative of the whole equation. Now we want to solve for cap f prime of x. So if we think about our algebra, all we've got to do is subtract big fx times g prime of x, move it over here, and then divide by g of x. So there's our subtraction step, and there's our division step. But it says in our instructions to find f prime of x in terms of f and g, not in terms of little f, little g, and big F. But we know what big F is. Big F is little f over little g. So I'm going to make that substitution. Now this is a compound fraction because we have a fraction in the fraction. And how can we make this better? We can make this look better by multiplying both the numerator and the denominator by g of x. If we multiply by g of x, distribute g of x across the numerator, I get f prime of x times g of x minus, and when I distribute g of x across this, the g of x's cancel. But look what happens on bottom. I have g of x times g of x, which is g of x squared. And we have actually just derived the quotient rule. So if I have f over g, then the derivative with respect to x of f over g is f prime g minus f g prime over g squared. So going back to thinking about my quotient as a function that's on top, so high, over the function that's on bottom, or low, we have low d high minus high d low over low low. That's the low function times the derivative of the high function minus the high function times the derivative of the low function over the low function squared. Or Santa Claus's version would be ho-de high minus hi-de ho over ho-ho. La la. All right, let's use that rule. Here we go. Here we have x to the fourth minus 6x squared over x cubed plus 5. This is my low function. This is my high function. Low times the derivative of high, I've gone ahead and taken the derivative of it, minus the high function times the derivative of the low function over low low. Now we have a low ha. And let's remember, all of this is following a negative sign. Here we go. If I FOIL this, we get 4x to the sixth minus 12x fourth plus 20x third minus 60x. Now that's that part. Here we're going to distribute a 3x squared over this, leaving it all behind the negative sign. And when we distribute the negative across, we get negative 3x to the sixth plus 18x to the fourth. And we can combine similar terms, and we get this as our derivative. X to the sixth plus 6x to the fourth plus 20x cubed minus 60x all over x cubed plus 5 to the second power. Leave that factored. Don't multiply this out. All right, pause the video and write all that down. Our next example, y is cosine of x over sine of x. Again, low d high minus high d low over low low. So that's sine x. Derivative of cosine is negative sine x minus cosine x times derivative of sine is cosine x all over sine of x quantity squared. And when we square a trig function, we typically write it like this with a sine squared of x. Now we want to do some work here. Notice that this positive times this negative gives me negative sine x squared and then minus cosine x squared all over sine squared. Notice that if we factor a negative 1 out of here, we get negative 1 times sine squared of x plus cosine squared of x, which is a Pythagorean identity. And we know that that is 1. So I now have a negative 1 over sine squared x, and guess what that is? Negative cosecant squared of x. That is our derivative. Y prime is negative cosecant squared of x. If we go back to the problem, notice that cosine of x over sine of x is actually cotangent of x. So what we just did was found that the derivative with respect to x of cotangent of x is actually negative cosecant squared of x. That is pretty cool. Now, number 6, example 6, we're going to use quotient rule. It says do this one 2 different ways, constant times a multiple and quotient rule. The easy way is constant times a multiple. Recognizing that, we actually have 1/7 times x minus 3. So I can take 1/7 times the derivative of x minus 3, which is 1/7 times 1. So y prime is 1/7. Nice and easy. Now, the other way would be to use our quotient rule. So our quotient rule would be low times the derivative of the top, which is 1, minus the top times the derivative of our denominator, which is a constant. So derivative of constant is 0 over low, low, 7 squared. So f prime g minus fg prime over g squared. And we can see that this will cancel out. We get 7 over 7 squared, which still is 1/7. When we look at the last example on this page, obviously the easy thing to do is to FOIL that function and then take the derivative. Pause this and write down what you see. On the final page, we see derivatives of trigonometric functions. You have to know these. Derivative of tangent is secant squared. Derivative of cotangent is negative cosecant squared. Derivative of secant is secant of x times tangent of x, and derivative of cosecant is the negative of cosecant times cotangent of x. Notice that the derivative of tangent is secant squared. This is going to always be non-negative. So that should tell us that tangent function is always increasing, which we know it is. The derivative of cotangent is negative cosecant squared. This will always be not positive. It will be negative. So cotangent should always be decreasing. So it's kind of neat. I have some little memory techniques here. The derivative of tangent is secant squared. I'll call it sexy, sexy. The derivative of secant is sexy tan, just a stupid little memory device. Also, you need to know your higher order derivatives. This is the first derivative, how we write it. Second derivative, y double prime, d squared y over dx squared. Okay. Third derivative, d cubed y over dx cubed. Very important to know that notation. And now the last example that we're going to look at is this one. Given f of x is 5x to the fourth minus 3x squared plus 2x minus 1, we're going to find the first, second, third, fourth, and fifth derivative. All right, first derivative, piece of cake. Second derivative is derivative of the first. Third derivative is the derivative of the second. Fourth derivative is derivative of the third. Fifth derivative, derivative of a constant is 0. Very nice. Let us remember acceleration is the derivative of velocity, and velocity is the derivative of position. So we now know that acceleration is the first derivative of the velocity function and the second derivative of the position function. Be sure to be able to show these relationships. Your TPs are for the quotient rule, problems 7, 11, and 15. See you next time.